At 7:15 a.m. on June 30th, 1908, a blinding bluish light tore across the sky above the Podkamenia Tunguska River in central Siberia. It ended in a massive flash and a pillar of fire that turned the horizon black. Scientists later estimated the explosion's yield at between 3 and 50 megatons of TNT. Even at the lower end of that scale, the blast was 1,000 times more powerful than the atomic bomb dropped on Hiroshima. The shockwave flattened 80 million trees across 2,000 square kilometers of forest. 40 miles away, the concussive force was still strong enough to knock people off their feet. The atmospheric effects reached as far as London, where the night sky glowed with such intensity that residents could read their newspapers at midnight by natural light. Despite this massive release of energy, the extreme isolation of the Siberian taiga meant the event went largely uninvestigated by the international community, leaving the true cause to remain a mystery for decades. It took nearly 20 years for the first scientific expeditions to reach the site. The remote geography and Russia's internal political turmoil had effectively kept the area a scientific cold case. Based on the reports of a fireball, researchers arrived expecting to find a massive, deep impact crater, the inevitable calling card of a large asteroid strike. Instead, they found an intact landscape with no crater at all. At ground zero, the trees had been stripped of their bark and branches, but they were still standing perfectly upright. The contradiction defined the investigation. A force powerful enough to level a region the size of Tokyo had somehow occurred without the impactor ever touching the soil. In the absence of a crater, fringe theories took hold. Some suggested a subterranean gas explosion, or even a disastrous test of a secret weapon by Nikola Tesla. The actual culprit was a 50-meter rocky body that triggered a meteor airburst before it could complete its journey to the surface. The asteroid entered at a shallow 30-degree angle, moving with enough speed that the Earth's atmosphere acted like a solid wall. Immense friction and pressure built up along its leading edge. As the atmospheric pressure compounded, the object began to fragment. Between 5 and 10 kilometers above the ground, the rocky body reached its breaking point and began to vaporize. The energy of this explosion funneled straight down. Trees directly underneath the detonation lost their branches to the vertical force, but remained upright, while the outward-moving shockwave knocked the surrounding forest flat. Those standing trees provide the exact physical footprint of a high-altitude, nuclear-scale detonation. This mid-air vaporization also explains the glowing European skies. If the object was a comet, the explosion would have injected massive amounts of water vapor into the upper atmosphere, creating reflective noctilucent clouds. Modern observations confirm this process. We see the same glowing clouds form in the water vapor exhaust plumes of NASA space shuttle launches. The final physical confirmation came nearly a century later, when researchers identified shocked quartz and melted silicate glass spherules deep within the 1908 biomass layer. These microscopic particles are the physical remains of the vaporized rock, serving as the definitive signature of the Tunguska impactor. Computer simulations now confirm the physics of the event. A stony object of that size would never reach the ground. The atmosphere itself is our first line of defense. Because the 1908 impact hit the desolate taiga, the sparse population meant human casualties were almost non-existent. However, the Earth's rotation meant the safety of civilization was a matter of timing. Had the asteroid arrived just a few hours earlier, the city of St. Petersburg would have been rotated directly into the path of the airburst. A few hours of planetary rotation are the only thing that stood between a remote forest fire and the destruction of a major metropolitan capital. The threat remains active. In 2013, the Chelyabinsk meteor provided undeniable proof that destructive airbursts over populated areas are a recurring reality. There are currently millions of house-sized objects sharing Earth's orbital space, many of which remain untracked. Designing a successful planetary mitigation system is a generational task. A report by the Task Force on Potentially Hazardous Near-Earth Objects suggests that a fully functional defense could take up to 70 years, a human lifetime to implement. The Tunguska airburst remains a 1,000 megaton reminder of the urgent need for a permanent planetary defense system.